It's a beautiful sunny afternoon in Hamilton, New York. Before leaving my house, I always grab my sunglasses. I love my polarized sunglasses. I used to have other sunglasses, which worked just fine to block dangerous UV rays and make things darker, but once I got my polarized sunglasses, there was no going back. They make everything look not only clear and sharp, but so different. There are so many things that look so cool. Come take a look through my glasses. As I walk down the street, I often tilt my head from side to side. It looks kind of funny, but I'm experimenting. Do you want to see what I see when I do this? I don't want to make you dizzy, so I'll tilt the sunglasses from side to side instead and keep the image upright. Let's start by looking at our lovely blue sky and tilt our sunglasses. The blue sky gets darker at certain angles and lighter at others, altering the contrast between clouds and sky. As I walk past the businesses in downtown Hamilton, I notice that the shop and car windows change their appearance as I tilt my head. Let's start with our sunglasses upright or vertical, then tilt or rotate them until they are vertical again. Watch the windows on the red car and black truck. Sometimes the front window has a lot of glare, and sometimes the side windows do. The glare on the shop windows behind them also goes away at certain rotations. Further down the road, Taylor Lake is a lovely spot with swans and plants and clouds. But let's look a little more closely at the surface of the edge of the lake. With my sunglasses on correctly, or upright, I can see the vegetation under the surface. But when I rotate the sunglasses, all I can see is the reflection of the clouds. Let's check that out again. This must be why sunglasses are sometimes called fishermen's friends. Let's see if we can figure out why we saw what we saw. We can start with a brief idea of what polarization is. Light is an electromagnetic wave with an electric field and a magnetic field. The direction of the electric field is what we call the polarization of the light. Our sunglasses have a polarization direction, which means that they will let through light or an electric field which is polarized only in a particular direction. When they are worn on a person who is standing up, like you would be walking down the street, the sunglasses are designed to let through or transmit light that is vertically polarized. When we tilted the sunglasses, we were changing the transmission angle of the polarizer. What we saw was that light reflected off of the windows or the lake or the sky disappeared. What was going on? Our observations showed that a polarizer blocked reflected light. Therefore, the reflected light must be polarized. At Taylor Lake, we saw a really obvious change in the reflected light with the sunglasses vertical and horizontal. Can you figure out in what direction the light reflected off of the lake is polarized? Right. Since the sunglasses only pass vertically polarized light, the reflected light that is blocked must be horizontally polarized. What about the car windows? Why were different windows darker on different polarizer angles? We can form a conclusion now from what we learned about the lake that is, in fact, true. When randomly polarized light reflects off of a nonmetallic surface like the surface of the lake, the reflected light is primarily polarized parallel to the surface. So, why are sunglasses polarized? Because they block a lot of the reflected light that we see. We have also deduced that reflected light is polarized and that it is polarized parallel to the surface it is reflected off of. Now, whenever you are wearing your polarized sunglasses and you see a change in what you are looking at as you tilt your head, which I know that you will do now, you know that what you are looking at is an effect of polarization.